All right. Good morning, everyone, and welcome to Developments in Advanced Recycling presented by TA Instruments. My name is Austin Talley. I'll be your host for today's session. Before we get started, just a quick housekeeping item. Today's session is interactive. We want to encourage you to drop your questions into the Q&A box located on the lower left-hand side of your screen throughout the presentations today. We've set aside some time to address those questions towards the end of our webinar. Lastly, we'll be sharing a PDF of both presentations after our webinar today. We're excited to have this discussion today with two industry-leading experts, Dr. Julie Rohrer and Professor Raul Lobo. Our hope is that the presentations today will continue to move the conversation forward around advanced recycling techniques. We know that these techniques can result in the better use of plastic waste for recycled products or energy consumption, and through these techniques, we can continue to bolster sustainability efforts without jeopardizing product, efficiency, and quality. First up, let's hear from Dr. Julie Rohrer, who is an Arnold O. Beckman postdoctoral fellow in the Department of Chemical Engineering at MIT and an incoming assistant professor of chemical engineering at the University of Washington. She received her PhD in chemical engineering from the University of California, Berkeley, and her BS in chemical engineering from Arizona State University. Her research is centered on utilizing heterogeneous catalysts to enable sustainable chemical transformations, including the synthesis of renewable fuels and chemicals and the catalytic upcycling of waste plastics. She'll be talking to us today about the advances in selective catalytic upcycling of waste polyolefins. Welcome, Dr. Rohrer.
Thank you so much. Thank you for the kind introduction and for this opportunity to share some of the work we've been doing in advancing selective catalytic upcycling of waste plastics. So because I am the first presenter, I have this opportunity to introduce why we're interested in advanced recycling of waste plastics. And first of all, plastics are ubiquitous in daily life. They provide great materials for consumer goods and products. They reduce food waste and improve safety for medical products, as well as providing a lightweight, durable, inexpensive, and low cost of transportation material. And this results in lower emissions compared to alternative packaging as well. And these plastic materials are typically starting from an extracted petroleum reserve, which we then use to create a monomer, which is then polymerized to the polymer. And at the end of the polymer's life, after it's been used for all these plastic applications, in a so-called linear economy setting, this would end up in landfills or leaking into the environment. So an alternative to keep the polymers in the economy would be mechanical recycling. But unfortunately, worldwide, only around 16% of plastic waste is mechanically recycled. And this is often melted and reformed into new products that eventually have lower quality than the original plastic material. And so this really just delays the inevitable disposal of these materials into landfills and leakage into the environment. And so as an alternative to that, we could use the polymer waste for fuels or energy generation. But again, this contributes to this idea of a linear plastics economy because we're generating carbon dioxide and that's being emitted into the atmosphere. So ideally, we could take these polymers and deconstruct them into some sort of useful product, monomers and new polymers. And this imparts circularity into the plastics economy. Or better yet, we could deconstruct the polymer into products that could be used to make new polymers and impart circularity there. And so there's a lot of different approaches towards valorizing plastic waste on the deconstruction side, specifically using different catalytic techniques. So on this figure here on the left, I have deconstruction of today's plastic waste into valuable products using either thermal, photo, bio, or electrocatalytic routes. And once we have these products, we can think about upcycling them into different upcycled materials, performance advantage plastics, or using them to create polymers that are intrinsically recyclable or recyclable by design. And what we've been really interested in is using thermal catalytic routes as a means to deconstruct today's waste plastics into useful products, specifically polyolefins, including polyethylene and polypropylene, and converting them into processable alkanes. These alkanes could replace petroleum-derived sources for the use as fuels or chemicals, or could be used to generate new polymeric feedstocks. But one of the challenges in using catalysis to break apart polyolefins is that they're comprised of these backbones of strong carbon-carbon bonds. And so there's been some different examples of thermal catalytic routes that have been enabled in order to activate and break these strong carbon-carbon bonds. And the state of the art that we might think about are pyrolysis and gasification, where in gasification, plastic waste is heated up and converted into a syngas, which can then be processed downstream. In the pyrolysis process, the plastic waste is heated up in an inert environment to generate a pyrolysis oil, which can then be later refined. And while these processes can work, they do offer low control over product selectivity, often suffer from the production of tars and chars, and require high temperatures, so from 400 all the way up to 900 degrees C. Alternatively, we can think about some milder deconstruction routes using catalysis. And a couple of them include olefin intermediate processes. And I won't go into a ton of detail about these since I believe you'll hear about them more in the next talk. But these are really exciting processes because they don't require molecular hydrogen to break apart carbon-carbon bonds, but they do require a sacrificial solvent and often require precious metal catalysts as well. What I'm going to be talking about today is the reductive routes of breaking apart polyolefins, including hydrogenolysis and hydrocracking, where you can take polyethylene and polypropylene at low temperatures, 200 to 300 degrees C, using hydrogen and break them apart into different products. This does require molecular hydrogen and precious metal catalysts, but hopefully I'll show you why these are some pretty exciting reactions. So as an overview of the talk, I'll first introduce how we came across ruthenium-based catalysts as being active for the hydrogenolysis of polyolefin waste, and then how we found that we could actually tune the catalyst to select for different types of products we might want to make, whether that be fuels and lubricants or targeting monomers for intrinsically recyclable materials. And finally, in the last few minutes, I'll talk about some emerging processes for upcycling mixed feedstocks and some of the frameworks to think about when we're handling realistic plastic waste. So to start, a couple of years ago, we identified ruthenium-based catalysts as very active for the hydrogenolysis of polyethylene. So the way that this process works is we have our model polyethylene substrate, we add it to this batch reactor in the absence of solvent. We add a 5% weight ruthenium on carbon catalyst and pressurize this vessel with hydrogen. And at 200 degrees C over 16 hours, what we are able to get is 100% conversion of our polyethylene to liquid and gaseous products. So the liquid products are a 45% mass yield of linear alkanes with carbon numbers ranging from C8 to around C30. And our gaseous products are primarily methane with some other light alkanes, including ethane, propane, and butane as well. And this is a very exciting process because we can see that this is done at only 200 degrees C. Compared to the 400 to 900 degrees C for pyrolysis and gasification, this is a much milder conversion. And in fact, this ruthenium on carbon catalyst also works for deconstructing polypropylene, mixed polyethylene and polypropylene waste, and realistic feedstocks. So here we went around the lab and actually found this polypropylene centrifuge tube, cut it up into little pieces, added it to our reactor along with our catalyst and the hydrogen, and after 24 hours at 225 degrees C, again in the absence of solvent, we can recover this 60% liquid yield of this nice liquid product that's comprised of isoalkanes, so branched alkanes, with carbon numbers from C5 to C15. But of course, when we think about real plastics, they're often going to be mixed together with all sorts of different types of materials. And so as a proof of concept, we took a mixture of both polyethylene and polypropylene and deconstructed it using our catalytic system into a mixture of branched and linear alkanes, where the linear alkanes come from cleaving apart the carbon-carbon bonds in the polyethylene, and the branched alkanes come from cleaving apart the carbon-carbon bonds in the polypropylene. And while this is very exciting and we published this work, we still have a problem, and that's that a lot of the carbon is being lost towards light hydrocarbons, primarily methane. And so by clipping a carbon off the end of the chain, we are creating this methane, which has a lower value and is also a greenhouse gas contributor. So we asked ourselves, how could we promote cleaving somewhere along the center of the chain as opposed to cleaving on the end of the chain? And there have been a few different strategies employed by our group and others in terms of trying to improve the selectivity for cleaving apart these carbon-carbon bonds. Where if we have polyethylene here, we can imagine that we want to cleave somewhere where these blue scissors are, somewhere along the middle of the chain to make our liquid products, whereas what we don't want to do is clip on the end of the chain to make the C1 methane product. And so some groups have been using platinum-based catalysts and this idea of enzyme mimicry to modify the active site environment of the catalyst to improve selectivity. And so this is a really exciting technique because you can avoid methane formation and really have more tunability as to what chain length of product you can get. Another method is to employ bifunctional acid and noble metal catalysts. And this can be done with platinum or ruthenium, as I'll show you, where you have a Bronsted acid and a metal that work cooperatively to actually shift the mechanism to a hydrocracking mechanism to improve selectivity towards liquid products. And so what we wanted to do was investigate a type of bifunctional metal acid catalyst using a zeolite support. So zeolite phagosite, FAU, is one of the catalysts that we studied, and this has high Bronsted acidity and also a nice pore structure that we can tune. And so by supporting the ruthenium nanoparticle on this phagosite, we can run the same reaction as the ruthenium on carbon that I showed you earlier at 200 degrees C under 30 bar of hydrogen. And this time we actually get a 79% mass yield of liquid products, and we still get some gaseous products with methane and light alkanes as well. But what's really exciting is that we see both linear and branched alkanes here. And these branched alkanes are a sign that we have the hydrocracking mechanism at play. And by supporting the ruthenium on this phagosite, by having this bifunctional catalyst, we increased our liquid yield by almost 2 times, so 79% compared to 45% over the ruthenium on carbon. And this effect shows up for polypropylene, hydrogenolysis as well, where if we compare the ruthenium on the phagosite catalyst at 215 degrees C, we can see a 54% liquid yield for polypropylene deconstruction to isoalkanes. Here's a little picture of the product as well. And if we compare that at the same conversion to an inert support, so a support without the structure nor the acidity, we see that we only get a 12% liquid yield. We're making a lot more methane formation, and we have mostly solids remaining. And so this bifunctional noble metal acid catalyst exhibits improved activity in liquid yield, lower rates of methane formation, and a narrower product distribution. But we still have a few challenges. One is that ruthenium is an expensive and not earth material. And 2, we're still producing a range of a distribution of products. What if we could target a single product that could be used to make new polymers and impart circularity into the process? So we sought out to do those 2 things, use a more earth-abundant catalyst and produce a narrower product distribution. And so we wanted to think about what type of catalyst could catalyze this reaction, and we identified cobalt-based catalysts as very interesting because these have been employed before for cleaving apart carbon-carbon bonds in the biomass and lignin depolymerization literature. And so we screened a variety of different cobalt catalysts on different supports. And what I'm going to show you here is that 2 of these catalysts stood out. One is bulk cobalt oxide, and the other is cobalt supported on a different zeolite called ZSM5. Here I'm showing you the phase distribution of solid, liquid, and gas. So we see that the majority of the products here are gas, and our hydrogen conversion over these, which is a metric for activity, is fairly high. And if we actually look at the product distribution of the gas phase, we can see that across all of the catalysts, we see this red bar, which is methane formation. So we're predominantly making methane, with the exception of the cobalt ZSM5 catalyst, which is selectively making propane, a C3 alkane. And this is very exciting because we are creating a more valuable product with high gas phase selectivity. And what's interesting too is that by supporting the cobalt on the ZSM5, we improve the catalyst stability. So if we look at thermogravimetric analysis curves of the cobalt supported on ZSM5 before and after the reaction, we see very minimal change or no change at all in the catalyst TGA curve. Whereas if we support the cobalt on an inert support like silica, we see all this extra weight loss for the spent catalyst. And this is due to coking and coke formation that deactivates the catalyst on the surface. And with this stable catalyst in hand, we can actually apply it to propane, or to the conversion of polyethylene and polypropylene and of different types. And so here with our reaction, again, no solvent, 250 degrees C with hydrogen pressure, we can convert low density polyethylene into propane, polypropylene, mixtures of low density polyethylene and polypropylene, as well as realistic post-consumer polyethylene. So an actual plastic bottle that we took from the lab, cut it up into pieces. And again, we have very high selectivity to this green bar here, which is propane. And what's especially exciting about the ability to take a variety of different plastics and create propane is that if you took propane and dehydrogenated it to recover the hydrogen, you can make propylene, which could then be readily polymerized back into polypropylene. And this really imparts this sense of circularity into the process. And so for the last part of my talk, I'd like to briefly go through a couple frameworks for upcycling mixed feedstocks. And here the ultimate goal is to take some sort of mixed plastic waste stream comprised of a variety of different types of polymeric materials and extract valuable products from that stream. And so the most common type of framework that we might think about is this idea of polymer separations and parallel single substrate chemical recycling, where we start with some sort of mixture of different polymers. Here I have green, white, and pink, and these are physically sorted into their different components. And then each of these different sorted materials are then processed to extract some sort of valuable product using different selected targeted chemistries or mechanical recycling that we might think about in a materials recovery facility. But an alternate to this is to think about this framework of catalytic fractionation of mixed plastics, where we start with this mixed waste stream, and then we use a series of catalytic processes to extract valuable products. So you can imagine the first catalyst might come in and selectively cleave apart the bonds in this white polymer here, which could then be separated into a valuable product. We're then left with the green and pink, which we could then attack the pink and cleave that apart, extract a valuable product, and so on and so forth until we have individual streams of valuable products from a mixed feedstock. As a little bit of an illustration of this, we could think about something like multi-layer packaging that might be made up of a few different types of polymers that are difficult to physically separate, where our first catalyst could come in and cleave apart more readily accessible CO bonds in something like PET to extract the monomer. We could separate that out. We're left with polyethylene and polystyrene. We can then go after the carbon-carbon bonds in polystyrene to extract the monomer styrene, separate that out, and then we're left with polyethylene, where we have a lot of different options for breaking this apart. For example, some of these hydrogenolysis and hydrocracking processes to extract liquid alkanes or propane. And what's exciting here is that we can also think about incorporating things like reactive distillation or other types of engineering processes to improve our selectivity and separations as well. Another thing to think about with separations is this idea of solvent-targeted recovery and precipitation. So the Huber group at Wisconsin has been working on using these solvent-based separation techniques to attack multi-layer films and extract individual polymers from that. So this is another example where we could integrate some of these solvent-based separations into this framework. And the last framework I want to talk about is the idea of deconstruction and downstream funneling, where we can start with mixed plastics, and there's a few different options here. So ideally, we could have some sort of universal catalyst that could take all the different plastics in the waste stream and break them apart into a single valuable product. Now, while that seems like a miracle, if we think about processes like gasification and pyrolysis, to some extent, they're taking a variety of different plastics and secreting a single product. Alternatively, this universal catalyst could break down this mixed waste plastic stream into a soup of deconstructed products. From there, we could then apply sequential separation steps to extract the valuable products, or we could think about using either a catalytic or biocatalytic funneling process that could take in all those different products and spit out a single valuable product. And so bioengineering is a really exciting tool here, where they're able to develop pathways that can take a variety of different types of products and spit out a single valuable product. And so to conclude, I hope I've given you a little bit of a flavor for the excitement of hydrogenolysis in the framework of chemical upcycling to produce higher value products from synthetic polymers, and how we can modify the catalyst to tune our product selectivity away from methane formation and towards fuel and lubricant production, as well as potential monomer regeneration, and how there's a lot of exciting new frameworks for thinking about processing mixed feedstocks. In terms of ongoing efforts, we're actively collaborating with the National Renewable Energy Laboratory to perform technoeconomic and life cycle analysis, and thinking about as well more fundamentally using theory and experiment and kinetic and mechanistic studies to enable tuning of product distributions. Maybe we want C4 or C5. How do we do that? By understanding the mechanism and then modifying the catalyst appropriately. And finally, thinking about moving away from platinum and ruthenium, moving away from cobalt towards more inexpensive and earth-abundant catalysts. So stay tuned for new papers coming out of the National Renewable Energy Laboratory, the MIT Raman Lab, and the Bio-Optimized Technologies for Keeping Thermoplastics Out of Landfills and the Environment Consortium. And finally, my own research group, the Roar Research Group, will be opening at the University of Washington, Seattle in January 2023. And we're going to be tackling a lot of different transformations in sustainable catalysis. And on the depolymerization front, really thinking about trying to develop methods that are depolymerizing plastic waste in the absence of both solvent and molecular hydrogen. So with that, I'd like to thank you all so much for your attention. I'd like to thank my colleagues at MIT and the Raman Lab, as well as our colleagues at NREL and the Stanford Linear Accelerator Laboratory. I'd like to thank the Bottle Consortium and the Beckman Foundation for funding this work, and of course, the organizers and sponsors for the invitation to speak today. With that, I'm looking forward to your questions in the Q&A session. Feel free to take down my contact information here, and thank you again.
Thank you, Dr. Aurora. Excellent presentation, and congratulations on the opening of your research group coming up at the beginning of the year. Again, everyone, please, there's been a lot of really great questions that are already coming in. Take a few moments. If you have any questions for Dr. Aurora, go ahead, head on over to the Q&A section, drop those questions into the Q&A box. We're going to compile those, and we're going to save those for the presentation at the end. Thank you again, Dr. Aurora. And now we're going to move on. We're going to hear from Professor Raul Lobo. Professor Lobo is a Claire de la Claire Professor of Chemical and Biomolecular Engineering at the Department of Chemical and Biomolecular Engineering at the University of Delaware. He obtained his undergraduate degree in chemical engineering at the University of Costa Rica in 1989, and later moved to California to pursue graduate studies in chemical engineering at Caltech. He was a postdoctoral fellow at the Los Alamos National Laboratory in New Mexico, and he started his academic career at the University of Delaware in 1995. His interests span the development of novel porous materials for catalysis and separations, the chemistry of zeolites, catalysis for energy and the environment, and the scientific aspects of catalyst synthesis. He has published over 200 referred reports, and he is a co-inventor of 9 U.S. patents. Raul is going to speak to us today about deconstructing polyethylene with no hydrogen. Professor Raul?
Austin, thank you very much for the introduction, and good morning, everyone. So I'm here to tell you about some of the work that is going in my group and my university in the chemical recycling of polyethylene and other plastic. I'm part, excuse me, let me see. I'm part of an EFRC center, which is funded by the Department of Energy, and it's called the Center for Plastic Innovation. And so in this center, we do a variety of chemistries related to transformation of plastic, not only recycling. And we feel that there are vast opportunities for innovation in this area of valorizing discarded products. And so right now, of course, what we do is that we mostly discard the plastics. Only about 10% of the plastic is recycled. The recycling requires sorting, and in the process, there's a reduction of value. And there is a little bit of emerging possibilities through the use of biological and chemical reconstruction of the plastic that is not commercially important. It's the area that we try to emphasize and grow. In addition to that, there are other streams that are important to incorporate into this sort of flow of materials, many of them coming from biomass. And so there's also work in the center that is trying to upgrade carbon that is derived from biomass and that can be integrated in the infrastructure that already exists for plastic production. this is a list of the principal investigators that are part of the center, and as you can see, is a large organization, including faculty from the University of Delaware, but as well as the University of Massachusetts, the University of Pennsylvania, the University of Chicago, and several others. We are organized in sort of 4 areas of expertise. Where I am is in the catalysis, synthesis, characterization, and testing. And I'm working with, for example, Professor Gorty and Professor Rosenthal and Professor Blahos at UPenn and University of Delaware and the University of Massachusetts. But we have experts in some engineering that are trying to develop catalysts and other biological systems that can process plastics in different ways. We have experts in polymer physics and polymer chemistry that are looking at the integration of all these chemistries into processes. And we have a group of individuals that do modeling at the multi-scale. So they look at what's going on at the molecular level to innovate in terms of catalysis, but also are able to do techno-economic analysis and life cycle analysis to understand the potential impact of the processes that we develop in the open market. All right, and so there's a hierarchy of polymers that we can work with. Of course, we can work with pristine polymers in the laboratory, but we can also work with extruded or 3D printed plastics, materials that have multi-layers, and the plastic that we use every day. And part of the goals of the center is to address all of them. All right, and so I'm going to skip this slide and give you an overview of the technologies that have been broadly investigated in this area. So there's gasification and liquefaction, that Julie mentioned before. And here the processes are organized in terms of temperature. In the graph, you can see that at the highest temperature, you have this pyrolysis chemistry in which you use temperature to break the carbon-carbon bonds. You can start and add hydrogen to the process in addition to a catalyst, and that gives rise to hydrogenolysis that occurs at lower temperatures, but that requires a catalyst that can be expensive to do this job. For instance, we have ruthenium on carbon that was mentioned before, ruthenium on titania, or more complex catalyst mixtures like ruthenium tungsten on zirconia. And there's also a hydrocracking in which the process of breaking the molecules are done similarly as is done in a refinery to take heavy oil and break it into molecules that are more useful as either as petrochemicals or as fuels, but that consume hydrogen. And here you can see some of the references that address these different technologies. From the point of view of recycling, chemical recycling fits within a hierarchy of processes that you can use to transform plastic waste. Here you have in this graph the concept of the primary or closed loop recycling, the secondary, that is downcycling of the polymer into smaller but less valuable parts. And then what we're trying to do here is tertiary, which is chemical recycling into molecules that are hopefully more valuable than the polymer that we're trying to transform. The thermal routes, like pyrolysis, require no catalyst. They are usually done in an inert atmosphere and at pretty high temperatures, and they are examples of what we call the linear economy, in which we use materials and then we dispose once after they have provided their function. Catalytic routes have the advantage that are more in synergy with the concepts of circular economy. They can operate in an inert, oxygen-rich or hydrogen-rich atmosphere, depending on the process that you're trying to do, and operate at much lower temperatures than the thermal routes that I mentioned before. All right, so in the group here at Delaware, we look at 3 main chemistries to investigate or develop processes for the chemical recycling of plastics. We look at cracking, and we look at hydrogenolysis, And what I'm going to talk about today is what we're going to call molecular mixing. And so for the point of view of molecular mixing, what we want to do is to mix a plastic like polyethylene with a solvent. And by combining pieces of the large molecules of polyethylene with the small molecules of the solvent, we obtain an intermediate product that is easy to process and upgrade in value, which could be in a refinery or in a chemical company. On the left, you can see a graph, and here what we showing is the composition of the plastic waste stream. And we have targeted the polyethylene because it's the largest component of this plastic waste stream. The technologies we are developing work both for linear low density polyethylene and for high density polyethylene. The advantages of molecular mixing are that they are less energy intensive, they can operate at relatively low temperatures, and that they require no hydrogen. And that's because hydrogen is difficult to handle, is expensive. Currently, of course, we make it mainly from fossil fuel resources, and so it produces a lot of CO2. And eventually, we can have green hydrogen, but in the meantime, we want to develop alternatives to avoid the use of hydrogen in the processing of plastics. And to that end, we want to use a reaction that is called metathesis, and this is the basis of molecular mixing. This reaction, or the investigators that developed this reaction into a practical processes and catalysts, received the Nobel Prize in 2005. And I'm glad to say that I was Caltech and received my polymer chemistry class from Professor Robert Groves, in which he actually gave lectures on the metathesis chemistry, which was kind of being discovered by them. So actually that was a very exciting time to be being a student in that class. But this molecular mixing of olefins operate in the following way. Here in the graph, you can see in red and in blue, two olefins that we're gonna sort of split with the catalyst, and then we're gonna generate new olefins that combines one section of one olefin with another section of the other olefin as indicated here, right? And so this process can be carried out using homogeneous catalysts as were developed by Professor Groves and Professor Truck, but they can also carry out using heterogeneous catalysts, which are, in this particular case, more amenable to scale up and processing. But what we really want to do is really not mix alkenes. We want to mix alkanes. And in order to do that, we need to add another component to this reaction mixture. And so when we're trying to mix alkanes or two different alkanes, we need to use a tandem reaction or a bifunctional catalyst. And so we are going to have two components, one which is based on platinum, and the role of the platinum is to remove a small amount of hydrogen from these alkane chains to produce a small amount of olefins as indicated here. Then this olefins is going to go to a second catalytic material. In this case, we're going to use a catalyst based on tungsten oxide that will do the metathesis chemistry. We'll combine the pieces of these olefins into new olefins as indicated here toward the right. And then we are going to use again the platinum catalyst to return the hydrogen that was removed at the beginning and transform the olefins in alkanes. So we start with alkanes and we end with alkanes, but we produce in the process a small amount of olefins that are the ones that really reacting and doing what we want, which is reduce the molecular weight of the polyethylene. All right, so here we're going to prove that this works in a vice form using just olefins. And so this is an experiment in which we're trying to mix hexadecene. And so we're going to take two pieces of hexadecene only over the tungsten catalyst. This is tungsten supported on silica to make new pieces. And the results are presented here on the right, where you can see that that we have still an excess of the C16, but we have generated a whole new range of other olefins that go in this particular case from about C8 all the way to over C30 and actually C36 and so forth. We can convert 95% of the C16 reactant at the beginning. And here you can see in the graph below, you can see on the basis of the carbon that we're using, the alkanes or the alkenes, an alkane that we are forming. And so we have very small amount of propane, increasing amounts of butane and pentane, hexane. We use heptane as a solvent, so that's not included in the graph, and all the way to molecules that are bigger than C16. So what the graph shows is that 40% of our product is bigger than C16, but essentially the rest, the other 60%, are species that are below in molecular weight to C16. All right, now we're gonna add the two components. I'm gonna have start with alkanes, have the platinum catalyst, and have the tungsten catalyst. And so we're gonna use all this stuff. We're gonna start with not with a polyethylene just yet. It's just a model which we're gonna use X-alkane. We're gonna mix it with heptane in the presence of platinum. The platinum will remove hydrogen, form olefins. The tungsten will mix these pieces to make a mixture of olefins of different molecular weight. And then the platinum again is gonna add the hydrogen. And here you can see in the results what happened in this particular graph. You have an internal standard, but as you can see, we start with C7 and C8, and we're forming, mostly alkanes. There's small amounts of olefins that you can see at the bottom of this gas chromatograph, but we're succeeding in combining these two types of alkanes. And so in this particular case, we had to add a new element that was very important, which is the presence of a zeolite. And this is the zeolite 4A that you are maybe familiar from applications in organic chemistry, which we use as an adsorbent for oxygenate. So it turns out that the tungsten catalyst or the metathesis catalyst needs to be reduced. And this happens spontaneously in the presence of platinum and even in the absence of platinum, because we remove a little bit of hydrogen from the alkanes, and that hydrogen is going to react with the tungsten to reduce the oxidation state of tungsten from 6 to +4, which is what you need. But this +4 tungsten is very sensitive to water and oxygenates like acetone and ketones that are often produced as a result of this reduction process. And so the role of the zeolite is important. If we don't have it, the activity of the catalyst is very small. But what it does is it traps all these oxygenates under the reaction condition, which in this case is in excess of heptane at 300 degrees C and an inert atmosphere of nitrogen. Here at the bottom, you can see that we managed to have a 90% conversion of the C16 hydrocarbon product that we put at the beginning. Again, we are not counting the C7 because we use that as the low molecular weight component of the molecular redistribution process. But you can see the molecular weight is kind of centered around the molecular weight of the solvent plus some extra amount, which is less than 25%, that contains molecules that are bigger than the reactant that we put in there. So we have done that now in low density polyethylene. And here I'm trying to illustrate the process, but it's again the same concept. We have a long chain polyethylene alkane and a short alkane. These are dehydrogenated in part in the presence of platinum. The metathesis catalyst mixes the pieces, and then we have hydrogenation again to obtain now a new mixture that's going to have on average half the molecular weight of the long chain alkane. So we keep doing this a number of times, and roughly on average, every time you go through this cycle, you reduce the molecular weight of the large or long alkane by half until we obtain a mixture of products that we can analyze at the end. Again, this is in a batch reactor, and the presence of the zeolite for it is very important to have a successful reaction. And these are the products. And so here you can see the liquids that are obtained. And so this is from gas chromatography. And in this particular case, we use decane as our sacrificial solvent. And so the molecular weight of the products that we obtain is centered around this alkane. You can see that the products are completely transparent and that we have what we can measure in GC, which is up to carbon numbers of 36. Right? We don't react, at least under these conditions, all the polyethylene, we react about 80%, and we retain about 20%, which is solid once the temperature is reduced. And what I show here is the result of high temperature GPC measurement in which we compare the molecular weight distribution of the virgin low density polyethylene that we use in this process with the product that we're obtaining that has much lower molecular weight. So these are species that have about 80 carbons or so in them. You can see from this graph that essentially all the polyethylene that we feed into the reactor has been processed or has reacted and has been reducing molecular weight by a factor of at least 100. In addition to all the products that we're making or that we record as liquid in this process. We generate a little bit of gas, but it's a very small fraction. And so because we don't make anything that has less than 2 carbons. So the smallest molecule that we make is ethane, but the ethane is present in very small amounts in the final product. And so we are in the process of still optimizing the reaction condition. There's many of them. We want to optimize the pressure, the temperature, understand what the impact of the feedstock purity on the process. The ratio of catalyst to polymer is important, and we haven't found the optimal yet. And what kind of solvents are the best solvents? So in this particular case, we compare C7 to C10 hydrocarbons as the sacrificial solvent. And the heavier solvent has a big impact, we think, because of the solubility at these high temperatures in the polymer is much higher for molecules slightly bigger than C7. So that's beneficial. The other thing is, and let me just go back here, is in order to make the process more circular, we want to then start to investigate how can we minimize the energy consumption of the process and how to use less carbon or smaller amounts of the sacrificial solvent. And so we're doing that kind of investigations at this time. As I mentioned, some of the members of the center here at Delaware do or investigate the hydrogenolysis of hydrocarbons, and in this particular case, they produce mixtures of hydrocarbons that have suitable molecular weights for what we want to do. And so we can envision now sort of a refinery for the processing of plastics in which we use some hydrogen to break down the polymer and make a liquid, and then we take that liquid and mix it to this molecular redistribution process with new polymer, such that the total amount of carbon that comes into the refinery is pretty much the amount of carbon that comes out as a product, favoring the circularity of the process overall. With that, I want to thank you for your attention and be happy to answer any questions. Thanks.
Thank you very much, Professor Lobo. Excellent presentation. Again, everyone, please feel free, head on over to the Q&A box, drop your questions in there. We've got about 15 minutes left, and I want to make sure I can cover as many of these questions as possible. We've got some really, really great ones coming in, and I'm super excited to be able to sort of go through these with both Dr. Rohrer and Professor Lobo. So what we're going to do is we're going to go back a little bit. We're going to actually start with Dr. Rohrer. We've got some great questions that came in for her, and I want to start with her. Dr. Rohrer, the first question that I have for you is, could you talk a little bit more about the framework of enzyme degradation and how that is different from catalysis?
Sure. So I don't do biocatalysis, but this is something that a lot of my collaborators and colleagues are working on. And I think it's really exciting to think about because the tunability that we have with biological systems and with heterogeneous catalytic systems is very different. The temperature operating ranges, reaction conditions, all these things are different. But there's this extra level of tunability that you have in engineered microorganisms. And so some of the work that some of our colleagues in the Bottle Consortium have been working on is these sort of multi-stage processes where you might have a thermal catalytic pre-processing step to generate some sort of feedstock material that the bioengineered organisms can then take in and use as their food, and then go through a different metabolic pathway to secrete a single valuable product. And so I think from my perspective, as someone who does thermal catalysis, it's important to stay connected with the needs of those downstream processes to think about how we can meet in the middle and develop processes to facilitate that handoff to enable circularity.
Great. And then the next question is the hydrogen used up or completely removed in your catalytic process?
Yeah, so we generally operate in excess hydrogen. So we have a slightly higher hydrogen pressure and more hydrogen than we need to actually convert all of the polyethylene. But essentially what we have to do is consume one molecule of molecular H2 for every carbon-carbon bond that we cleave. So we could run this in an excess of hydrogen, or we could run it in a hydrogen limited scenario where the reaction essentially stops once we've consumed all of the hydrogen. Yeah.
Awesome. And then I'm going to combine these next two questions because I think they're kind of related. The first part being, what's the cost analysis for doing chemical recycling process at the industrial scale? Are there companies that are already doing this type of recycling? And then the second part of it is, what do you think is the most interesting economical method for upscaling with a process like this?
Yeah, that's a great question, and one that I don't have a great answer to yet, but what I can say is that we're actively thinking about modeling the techno-economics of these processes. So we have collaborators at the National Renewable Energy Laboratory who are experts in both techno-economic and life cycle analysis. So they're thinking about putting in all the inputs, what's the feedstock cost, what's the cost of the hydrogen, the solvent recovery, and actually putting these into models that can tell us what the economics of the processes are going to look like, and how we can compare those to other existing processes that are being implemented at larger scales, for example, pyrolysis, gasification, and liquefaction. And so I think that from the fundamental side, it's important for us to be thinking about these different bottlenecks that might be coming up so that we can adjust our investigations appropriately.
Great. Do you think this process would only work for solid plastics like PP, or also for, hydrogel, aqueous, petroleum-derived plastics like polyvinyl alcohol?
Yeah, so when we work with polyethylene and polypropylene, of course, they're solids at room temperature. Once we bring them up to reaction conditions, they are a polymeric melt. So they are sort of a liquid. And so I don't think the phase of the polymer is an issue. I think where we run into some problems could be when there's different functional groups present on the polymeric chains that might interfere with the catalytic activity. So things like OH groups, those might not have too much of an effect unless we have significant effects of water that might result from dehydration of the chain, for example, or a lot of oxygenated functional groups. Those might not affect the hydrogenolysis too much, whereas they might affect some of these other types of catalysts that are not stable in oxygen. Things like PVC, those will cause a lot of issues because of the halogenated heteroatoms that could poison the catalyst and potentially create toxic byproducts.
My next question is, have any interferences been observed from common plastics additives such as, antioxidants or heat stabilizers?
Yeah, so this is something we're really actively working on investigating to see what the tolerance of these catalytic systems is to these different types of additives. And so like I mentioned, things like PVC, those are going to cause some problems with deactivating the catalyst, but other types of CO-containing linkers and things like that, these are kind of an ongoing point of investigation.
Nice. Could you describe the bath reactor and what plans do you have to design a continuous, depolymerization reactor? I mean, what challenges do you foresee in going to a continuous reactor?
Yeah, so the batch reactor is essentially like a mini glorified pressure cooker. We do these things on about a 1 mil substrate scale, so this is very much a lab scale. In terms of scaling it up, for our techno-economic analysis, we've been thinking about how this might be done in a flow process. I think there's a lot of challenges, and a lot of those are centered on the high pressure of the hydrogen, as well as the fact that to introduce plastic in a flow system, it has to be a polymer melt. And so there's all sorts of different transport considerations and reactor engineering considerations to think about actually flowing a molten polymer through a flow system when you're operating under hydrogen pressure.
Great. And then the last one I'll give you, what are your thoughts on the supercritical solvent-based recycling, that's currently being developed, for instance, by the PNG technology being commercialized by Pure Cycle Tech for polypropylene? They're saying the bonds aren't broken, so technically it's mechanical, but without the downcycling nature of traditional mechanical recycling. How would you compare the advantages or disadvantages of this process to the ones you talked about today?
Sure. So my understanding there is that it's really exciting because you can recover a more pure form of polypropylene without having to deconstruct it and reconstruct it again, right? So that saves you some energy, but also enables you to clean it, purify it, and lower some of the concerns with mechanical recycling where there might be contaminants and additives and things like that in the polymer that lower its properties when you try and mechanically recycle it. I think in terms of comparison, when we think about modeling the economics of these, there's never going to be a process that's infinitely recyclable. As soon as you continue to recycle a material, there's a sort of end lifetimes associated with that transformation. And so that's going to depend on what the original plastic is and the energy required to run these sorts of recovery processes. So I definitely think it's exciting, but I think that we really need to diversify all the different methods we're using to think about how to chemically recycle or mechanically recycle plastics, such that they work for a variety of different feedstocks.
Awesome. And I do want to squeeze in just one more question here. How can we introduce biological recycling to a mechanical process to improve the circularity of plastics?
That's an interesting question. And I think, again, it goes to this idea of biological pre-processing step to clean a feedstock to make it readily accessible for a thermal catalytic process, or using it downstream to upcycle a deconstructed product. Since it's not my area, I don't know specifically what kind of efforts are being involved on the mechanical recycling side. But I think it's certainly an interesting question and something that we could talk more about offline if you'd like.
Awesome. Well, thank you very much for that, Doctor. Really, really appreciate it. I'm going to jump over and give Professor Lobo just a little bit of time to answer a few questions that have come in for him. Before we jump in, everyone, continue to submit your questions. Continue to submit your questions. We may not get to all of them today, but we'll give you all the resources to be able to reach out to us, get your questions answered, and get back to you if we don't cover your question today. Professor, I want to jump right into, are you concerned, sorry, one moment. So I'm just rereading this question. Have you ever thought about modifying the monomers obtained in the reactions into biodegradable monomers to synthesize biodegradable polymers?
Yes, we have thought about that. I don't know if we have a solution. We have thought of combining, let's say, the metathesis chemistry to make molecules that have diacid groups in the end, so that we can have sort of a polyethylene made of some sort of macromonomers that will behave like polyethylene, but that can be chemically recycling the way we do that with polyesters. But we have not yet to succeed to do this chemistry at the laboratory scale. But that's a very actually valuable suggestion and something that we're thinking about.
Here's an interesting question. If one uses pyrolysis to produce a liquid fuel, which can then be sent to a refinery for further processing, why is that not considered participation in a circular economy?
If it is sent to a refinery to be reprocessed into a new product, it is part of a circular economy. So I think we study pyrolysis as well. What we're trying to do is to combine pyrolysis with catalysis to make a different suite of products than the ones that are normally obtained from pyrolysis. But pyrolysis gives you a very broad distribution of products, and with the presence of a catalyst, you can narrow down into something that might be either easier to process or that might have already value from the get-go. But I think I don't see a reason why pyrolysis has to be removed from the analysis. It's just that it requires very high temperature and it consumes a lot of energy.
Got it. Are you concerned about depolymerizing PVC and the production of harmful byproducts that might be generated?
We're very concerned about PVC because the chlorine is toxic to our catalyst. Yes. And so what I can tell you is that there are ways of pre-processing the polymers, so if there are contaminants of PVC can sort of be removed, and we do that by reacting the PVC with bases such as magnesium oxide, and what you produce there is magnesium chloride, and then a stream that is essentially free of chlorine. And so there's ways of addressing that, but requires a pre-processing step.
Can the thermocatalytic processes be used to produce multimodal polyethylene instead of complete gasification?
Yes, I'm not working in that research, but if you look at the research of Professor Blajos, which is also here at Delaware and is part of the center, he and his students have developed a sort of hydrocracking catalysts that are able to do that, right? I don't know if he's making the multimodal polyethylene species in the sense that you're thinking about, but he can make products that are at least bimodal in their molecular weight distribution, and that might be beneficial or not depending on what applications you have in mind.
Got it. How would you say, how does LCA and environmental impact compares between mechanical and chemical recycling?
I think that if you have a stream that is pure enough, you should look at mechanical recycling first and then go to chemical recycling second, because I think the investment is much higher, the energy consumption is much higher. Now the potential of making products that are more value is high as well, but the investment is going to be higher. And so I think mechanical recycling is here to stay. This is not a replacement, it's an addition to a mechanical recycling that we should implement to reduce the amount of plastic that we're sending to the landfill.
Great. And we've got just a couple more minutes, so I want to make sure I squeeze in these last two questions. The transformation of PE waste into waxes, is that applied? Can that be applied at an industrial scale?
Can you repeat the question or give me the question number?
Sure. It's so they're asking the transformation of PE wastes into waxes. Can it be applied, or is it applied at an industrial scale?
No, the molecular weight distribution is applied in refineries, and what they do there is that they combine hydrocarbons that are relatively heavy with the excess hydrocarbons that refinery might have, let's say C5s, to make more fuel-friendly molecules than these two, but it's not used in the sense that I mentioned in the talk before. And it's usually in continuous processes, which is in a refinery is easier than when you have to work with solids. That's the case that we have here.
Got it. We're at time. We're coming up on time. So I just want to say thank you again, Professor Lobo and Dr. Rohrer. I really, really appreciate your insights. Obviously, there's a lot of people here who want to continue the conversation. We've got a lot of really great questions that we weren't able to cover today. So again, everyone, I want to encourage you, continue to drop those questions in the Q&A box. If you have questions that you want to send out to us, we're going to provide our email, so you can always reach out to us at info@ta-instruments.com. You can visit our website, join our LinkedIn, Facebook. Also, I'm going to give you the speaker's contact information. If you'd like to reach out to Dr. Rohrer, you can reach her at Rohrer, that's Rohrer, at uw.edu. And then you can also reach out to Professor Lobo, that's Lobo, Lobo, at udel.edu. So if you've got more questions, if you'd like to continue the conversation with us, please feel free, reach out to us there. Just one final quick housekeeping thing for everyone. We're going to be sharing the slides in PDF format after the webinar today, so be on the lookout for that. And then, of course, be on the lookout for our upcoming webinars. Our next webinar is entitled Breaking Down Thermosets. All right, we're going to be having that on November the 10th at 10:30 Eastern. Look out for the opportunity to register for that very, very soon. Again, thank you so much, everyone, for joining us. Thank you for spending time with us today. Thank you again, Dr. Rohrer, Professor Lobo. We really, really appreciate your insights on this topic, and we're super excited to keep pushing and moving the ball forward. Thank you again for everyone. Have a great rest of your day.